to continue on with examples of electrophilic aromatic substitution reactions. Now we take nitration. How we can nitrate benzene? Benzene is actually nitrated with a mixture, or it can be nitrated with a mixture of nitric acid, HNO3, and sulfuric acid to give nitrobenzene. So this is the product, nitrobenzene, the product of this nitration reaction when benzene ring reacts with a mixture of nitric acid and sulfuric acid to give nitrobenzene. Now, if you look at nitrobenzene, clearly the electrophile that's required is actually NO2 plus the nitronium ion. That's the electrophile that is involved here in this electrophilic aromatic substitution reaction. So it's obvious, therefore, that nitric acid and sulfuric acid react with each other initially to give the nitronium ion the required electrophile for the nitration of benzene in this electrophilic aromatic substitution reaction. So how can that happen mechanistically? Let's show that. This is the lowest structure of nitric acid. This is nitric acid, HNO3. This is the lowest structure. Please note the charges and, of course, the types of bonds here. And this is sulfuric acid. This is sulfuric acid. This is nitric acid. So what can happen probably is oxygen picks up a proton from oxygen in nitric acid, picks up a proton from sulfuric acid. In other words, it gets protonated. So this can happen. So we take a lone pair from oxygen here in nitric acid. We make a bond between oxygen and hydrogen. The hydrogen-oxygen bond is simultaneously broken. We make a double bond here between oxygen and sulfur, and one of the sulfur-oxygen double bonds is simultaneously broken. If this happens, then this is what's obtained. This protonated nitric acid as one product, of course, in addition to the conjugate base of sulfuric acid, which is the hydrogen sulfate. So that's also obtained here. So this is the HSO4 minus, the conjugate base of sulfuric acid as a result of course, this acid-base reaction or protonation reaction of the OH group in nitric acid. Now, in order to form the nitronium ion, we can actually take one of the lone pairs on this this is a negative charge, on this negatively charged oxygen. So we take one of the lone pairs here, we make a double bond here. So we take one of the lone pairs on the negatively charged oxygen, we make a double bond between oxygen and nitrogen, and the nitrogen-oxygen double bond is therefore broken. That's because this protonation step makes the OH an excellent leaving group, of course, which is water. Water is an excellent leaving group, and that's exactly the point or the objective here is to lose OH, but OH can only be lost in the form of water, which is an excellent leaving group, and water can only be formed as a result of protonation if you like, an alcohol in general reacts with an acid. So protonation followed by departure of the leaving group, if you like. Now this gives this intermediate, which is nitronium ion. Still the formal charge, of course, on nitrogen is plus, and of course it's NO2 plus of course H2O that are formed in this reaction here so far. So this is the nitronium ion, the electrophile that's needed in order to react with benzene in this nitration reaction. So the nitronium ion then gets attacked by benzene This is the benzene ring, which then attacks the nitronium ion at nitrogen, of course, and the nitrogen oxygen double bond is broken. And of course, remember, this step is slow because that's when benzene loses aromaticity. That's exactly why it's slow. So this is the intermediate, the carbocation intermediate that is formed. Remember, nitrogen has a single bond with oxygen, a double bond with another oxygen, and the formal charge is always +1 because here there are 4 valence electrons from the usual number of valence electrons, which is 5, so that's +1. This carbon, of course, there are hydrogens here. This carbon must have a positive charge. Now, the hydrogen sulfate, or even water, but we can use the hydrogen sulfate to come and pick up that proton. The hydrogen carbon bond is therefore broken, and a carbon-carbon double bond is formed to give the nitrobenzene product, which is this one here. So this is nitrobenzene. Remember, this is fast, this step, and remember, this step is slow. And of course, slowness or fastness, that's due to thermodynamics, basically. Benzene here loses aromaticity, therefore this step is slow. The carbocation intermediate, again, regains aromaticity, so therefore this step is actually fast. So the nitrobenzene is formed as a product. So this is an example of a nitration reaction of benzene when benzene reacts with nitric acid and sulfuric acid. And remember, the electrophile is the nitronium ion that is required. This is the nitronium ion. So this is an example of a nitration reaction of benzene where benzene reacts with a mixture of nitric acid and sulfuric acid to give the required electrophile, which is a nitronium ion, and eventually nitrobenzene is formed as a final product. This is another example of an electrophilic aromatic substitution reaction.